Hi everyone, good morning, and thanks for joining today's Qflow Spark on Kubernetes call. And today's date is 20th February, 9:05 a.m. PST. Um, we got an exciting topics, especially the demos, and I guess we have 1 hour and see how much of this can be covered, all these three topics. Um, so yeah, if there is any spillover, we'll move it to the next week. If not, um, so the very first topic for today's meeting is Spark Native Remote Shuffle for high reliability and cost optimization. It's actually an interesting topic and would love to hear how that works. I think we have Salesforce team who's going to present this today from Siddharth's team, and we have Karupaya, if I'm pronouncing correct, right?
Yeah, you did. Yeah.
Yeah. Nice to meet you. And then we have two more topics: Apache Data Fusion plus Comet benchmark results. That Manabu has done some work around running the benchmarks and comparing with some of the results, and he's going to share. And then finally, Apache Caliban best practices, and see if we get some time to the third one. But otherwise, we can move that last topic to the next week. So with that, before we kick off the topics, and I would like to anyone who joined for the first time, you want to come on camera and if you don't want to, or come on a mic and introduce yourself. That would be good. Quick intro.
Yeah, I can go first. I mean, this is not my first, but yeah, I have not introduced myself before. So, I am Karupaya. I work for Salesforce. I work on the Spark team at Salesforce. I focus mainly on the performance aspects of Spark at Salesforce. And yeah, that's a very brief introduction about myself. Yeah.
Yeah, thank you, and love to hear more about your demo today. Anyone else who wants to introduce yourself? You already introduced in previous meetings, so but that's okay. Tariq, Chitrangan.
Earlier, I did introduce myself a couple of times. Yeah.
All right, okay. Nice to meet you. Uh, right, with that, we can kick off and maybe we'll give is there something that you want to share the screen, Karupaya?
Yes. Yeah.
Okay, I'll stop sharing the screen. You can take over from here.
Yeah. Are you all able to see my screen?
Yep.
Sure. So let me get started. So today I want to introduce Shuffle Vault to this group. Basically, this is I would say yet another attempt towards disaggregating Shuffle storage and compute. So basically, like I mean, I don't want to go into details of how I mean how we see the dreaded fetch failed exceptions and having to recompute the jobs, etc. I mean, this problem has been there for quite a while now, and we also know what's the ideal solution. That is a disaggregation of the shuffle storage from the compute nodes. And there has been multiple attempts in attempts to I mean not attempts, and they are still very good solutions. Like there has been this magnet push based shuffle, which is basically yarn based, and I mean a yarn oriented, where you need an ESS to be deployed. And there is this Celebron, there is the Unifull at Meta, etc. So, but all of these solutions require an additional distributed system to be hosted, like provisioning the hardware, having to maintain the separate system in itself. Plus, also you need the knowledge to actually maintain these systems. I mean, knowledge of the Calibron or Unifil to be able to tune them to uh, be robust. Uh, I mean this though these are all very good solutions, but for very small teams or someone who doesn't want to maintain these and not have the resources to spend on maintaining these systems, this is not an easy decision to take, like having to deploy a Calibron or Unifil. Uh, so that is that, and there has also been other solutions in. There is this IBM's Spark S3 Shuffle, which tries to write to S3 directly, but this also has some drawbacks related to the total number of requests that are being made by me being made by the shuffle manager to S3, which eventually gets to throttling, etc. And throttling is one, and given the number of requests to shuffle, and given there is a cost involved to these requests, this becomes a big chunk over a period of time. Yeah, I mean, and also there is natively in Spark also there is this shuffle like migration option, wherein when a executor is being decommissioned, you can put these shuffle blocks to S3 or any remote storage and being able to retrieve this. But it doesn't solve the complete problem of like fetch fail exception. There could be scenarios wherein the nodes can go down even before the shuffle is uploaded. But this is the brief background of what the solutions are, and the main thing that I am coming at is the operational overhead that's involved in maintaining the system, the uh, the resources that are like in terms of cost, resources, and the knowledge that is required, and in terms of the native solutions that's currently available. Native, when I say native to Spark without having to deploy a new system, these are not complete solutions. These are more like some things that will help you, will might help you, but not always. So that is the background of why I am going to uh, give a native solution for the shuffle problem. But before that, just want to pause to see if you had any questions. Yeah, I'll keep going then. So now we know that this given the operational overhead, etc., the ideal solution will be for Spark to write directly to remote storage. But like I highlighted briefly, there was an attempt already wherein the native shuffle code that is there in Spark, when it writes to S3 directly, it has its own pitfalls in having to make a very large number of requests in a way, like, and which can result in throttling and also can increase the cost significantly. I mean, I'm not going into. I have one section in comparative analysis of Spark S3 Shuffle, which does this already. I mean, I will share this document for I mean future reading. But in terms of comparing how my solution is going to reduce the number of requests, there in a better solution than what is existing. So the proposed solution here is, I mean, let me tell the current state of things, then go back to. So here this is the current state of shuffle. So the mappers generate the shuffle data on the local store, and then the reducers read from every other mapper for the data for itself from every other mapper. Uh, Now with my proposed solution, what I'm trying to do is I add a new stage called consolidation stage, which this is the mapper stage, and it still writes shuffle data to local storage, but the additional consolidation stage reads for every reducer, it reads all its shuffle data and then consolidates into one file before writing it to remote storage. And the subsequent reducer that comes in just reads that one single file from S3 and then operates on top of it. So now the difference here is the total number of requests. I mean, just for the sake of discussion, it will be just one request to upload and then one request to download the same file on the reducer side. I mean, it could be multiple based on the size of the file, etc. But as I mentioned, it's for the discussion purpose. I will keep it simple. So this is what I mean will make it robust in terms of using remote storage for shuffle. So, I mean, I would like to pause at this point to hear uh, any questions.
Yeah, so I do have one question. So are you referring to the Cloud Shuffle plugin created by AWS Glue before? Have you heard about that?
No.
Okay, so there is uh, a Cloud Shuffle plugin, but I'm not sure if it's very popular. Um, I haven't tried that myself, and I'm just leaving it here. So uh, it's an open source
Uh,
project that AWS created this. It's called S3 Cloud Shuffle plugin. Um, you can use this, which can write your shuffle data to S3. But what I
uh,
heard, go on, go on.
no, I think I have read about this
Yeah.
already.
Oh, okay, okay. Hmm. Okay. So I would like to know a bit more about comparison. If you know the solution, how that is different from this one.
Uh, I mean, it was fundamentally different, so I didn't do
Okay,
a
okay,
comparative analysis, but
okay,
I mean, I can I can look at it and then get back to you. Yes.
okay, perfect. Yeah.
So yeah, I think I will go ahead and then if there is any questions, I will take it. But now with this solution, the main one big concern for one big concern that would come up is this shuffle consolidation stage is another stage that would take some more processing time, and this would impact the that might be one big concern. But uh, it is not always the case because the shuffle consolidation stage is not memory intensive or compute intensive, and even if there are millions of records, since it is not compute intensive or memory intensive, this is going to complete in a matter of seconds. But still, this is going to like if there might be concerns that this will increase the performance by a couple of seconds, right? And like in a typical cluster, there are always most likely always free cores that are available, while there is some other process that is blocked on a prior stage. So these cores can operate in parallel to do this consolidation. So where I'm coming at is like over the if you look at the overall time of a query, the time taken for the shuffle consolidation is generally amortized over a longer period of time. That said, the second question that might come up is, will this always be useful even for smaller shuffle data? So we are mainly trying to see if trying to avoid fetch failure exception, the probability of query completing within probability of shuffle fetch failures in a span of 5 minutes, or I mean for a very smaller query which generates very small shuffle data is very minimal. So this solution will help queries that run for longer time, like more than 30 minutes or something. But this also brings in the question of, should a user know how long his query has to run before trying to opt in these solutions? The answer is no, because this has been integrated into the adaptive query execution pathway of Spark. To at runtime, this framework can determine whether the shuffle data is how big the shuffle data is, and based on that, it will switch between the shuffle vault and the local storage dynamically at runtime. So there won't be any user intervention. Uh, are there before continuing? I just want to take a pause to see if there are questions.
Where is the consolidation happening? Is that happening in memory or like on disk?
It's happening on in memory.
Okay, so then you're not storing everything in memory, right?
No,
Or
it's actually streamed.
okay. That way you don't have to worry about it. Oh, I see. Okay. Then the constraint would be networking then, if you were to store this in like S3.
Yes, yeah.
Okay. So then if you were to
Yeah,
use
so
this one,
that's why I mean the constraint is network based on the total how big the shuffle after consolidation, how big the size of the shuffle is. Yeah.
okay. So then it's possible that you might get slowed down because of the like an EC2 instances not having enough bandwidth or something like that, right?
That is correct. Yes. Yeah. That might be the problem, but in general, like the core to network bandwidth ratio is generally higher, and it would in my opinion, I think it's not a very big problem. Big yeah.
I see. And then is there like a fallback mechanism of some sort? So like say example, when you're transferring data to S3 and that fails somehow, like the executor dies or something. Is there like a mechanism to make sure, it resumes or like, deletes the old data or anything like that?
No, this is something that's on the roadmap. The shuffle data that was before consolidated is still there on the local nodes. So during adaptive execution, we will be able to determine whether a particular thing failed or is failing, and we will be able to remove this consolidation phase completely and then continue with the original shuffle manager of native Spark.
So just to understand better, so across two nodes, you have a bunch of shuffle files, and you are um, uh, consolidating shuffle files across both the nodes, and then try to remote storage. So it's something like a streaming, right? Like you wait until the data is written to an S3 successfully. Once it is written in S3 or whatever the end storage, that's when you go back and remove those shuffle files from the existing nodes, or during the process you will remove those files. That's what I'm thinking, because
No,
that's.
I I think once the data is returned to S3, that is when
Mhm.
we will downscale the nodes that had the the original shuffle data. Before that, we only after writing to S3 have we made it durable and in a way like I would say checkpointed. At that point, you don't need the executors which actually generated the data. But I would still keep that as a fallback in case
Mm,
if we see that we are going to use. I mean,
yeah,
if we see that we might require these local blocks for uh, I mean better
until a
code.
guaranteed right,
Yeah.
right? So until a guaranteed right, and you might want to keep the shuffle block, and if something fails, so that can be reused. And the second thing, I think, going back to the same question, a lot of the shuffle data are in terabytes sometimes, right? Uh, and consolidating, do you have any limitations on what this size that you want to make it? You're making it a single file, right?
No, it's a single file. That is correct. I think, but like Manabu asked, like this is streamed, and we will chunk this into. This is a configurable value of
Hmm.
128 MB, and then we
Okay.
will keep appending to the existing file on the remote storage.
Okay.
I mean, unless, but that's a good point. Like on having to have a size on the shuffle blocks, but given that it is streamed, we will not know the size of the actually,
Yes.
we will
Yeah.
know it because it's already generated, and we will have this information in the driver to get the size, total size of the shuffle.
Yeah.
But if it's a constraint on the remote storage to not be able to store a file of particular size, then we will have to break this up. Yeah, but
Exactly. I think probably the efficiency when it comes to the reading back from S3, like if you uh,
no,
chunking to 128 or chunking to 512 MB or the right sizes are quicker to read from S3
no, even when reading, I think we will not read it like if it's a
as an
1 TB file, we will not read it 1 TB file.
mm,
Uh,
mm.
Especially, I mean, we will read it in some chunks. And you also brought a good point, right? Like I think that this also means that now we have unlimited storage. The probability of space going out is also avoided from having had stored in a remote.
Yeah, yeah, 100%. Definitely. I think this sounds very interesting. Keep going so we can keep some question to the end.
Yeah, sure. Yeah. Another important question that will I would like to answer is now in this image, like we have store the mappers have written the data to local storage, and there is a consolidation phase. Now, what happens if the mappers have written the shuffle data to local store? Now, the consolidation stage is not scheduled immediately after the mappers have completed writing their shuffle data. So the window, I mean, eventually it will get scheduled, but there can be a big, I mean, it could be a like 1 hour window or 2 hour window before the consolidation stage could be actually scheduled, which means that we have brought in a window where there could be these nodes could be taken down, and we might have to regenerate, etc. So to avoid this, I also have made some. I mean, my proposed solution has been to use a scheduler which will try to schedule these stages immediately after the mapper generates the shuffle data. So that way, as soon as the mapper generates the shuffle data, the consolidation stage is scheduled, and the window of loss is made to be very, very small so that the shuffle is durable as soon. So that, and I have mentioned about this in the in. I mean, yeah, I have mentioned this in the one of these sections, but yeah. So, I mean, I think I also covered some of the challenges and mitigations on how adaptive execution can be used to be able to determine at runtime whether a shuffle needs to be uploaded to S3 or not. Uh, yeah, I mean, this is the section that I was mentioning about how much of network requests that we will avoid by having to do this. Yeah, another important thing is about one thing is about making the shuffle durable. The other is about having the now we have an opportunity to take away the nodes that generated the shuffle and reduce the cost. So no longer the node on which the executor was running needs to be up and running to be able to serve the shuffle data, because now the compute nodes can go away given we have moved it to remote storage. This will basically we will be this enables us for aggressive downscaling of the nodes or the compute nodes. In I would like to mention about the current status before going to the demo. So I had created an SPAP in Spark, but there were some concerns around it. I mean, this is mainly coming from like Calibron already supports this. I mean, if we have a deployment of Calibron or Uniful, we will be able to solve the same problem. But like I mentioned initially, this is the having to deploy Calibron. It has its own operational overhead and cost overhead plus the resource overhead. So that is the reason a native solution will work better if for many use cases. That was that. And I have a PR open in the open source also, which is I mean, you can just fork off it and just build it, and it should work out of the box. I'm going to show a quick demo on how it works. And yeah, in the next steps for me is also to given there is some pushback, I am planning to make this pluggable so that even without having to make code Spark changes, we should be able to use it. So that is the plan. Now, I would like to go to show a quick demo on how this works. So I mean, this is mainly would be a representative of what the diagram that I showed you. I mean, that won't be much thing new. I'm just going to go the Spark UI to show you what happens. So here in my command, I like I mentioned, I have a new scheduler mode which is called weighted FIFO, and then I have made the consolidation size threshold to 0. What this means is whenever the shuffle data is more than of size 0, just consolidate. I wanted to make sure in the demo it is always consolidated, so I have made it 0. So yeah, this is the store. I mean, I am using my local storage as the store where the shuffle will be stored. Ideally this should be an S3 path or an a Google Cloud path. And yeah, and I have my own shuffle plugin to be able to write to both local and S3. So yeah, I mean, this code is actually very simple. I mean, I have a table on my local, which is table A, table B, and then it has 100,000 rows, and I am keeping the shuffle partition size to 2 just for the demo. And I have enabled shuffle consolidation, and I have disabled broadcast because with the broadcast you there won't be any shuffle. So I just wanted to make sure it is disabled, and just doing a join to make sure there is a shuffle, and let's see what happens. Now this query ran. Now let me open the Spark UI. So this is the table 1, table 2, and it did an exchange, which is the shuffling. And here you see another node called consolidation exchange, which actually read the all the data from uh, all the data from shuffle data from the previous node, and then consolidated into one block and then uploaded to S3. Both of these nodes do that. And this sort node, which is the part of the sort merge join, reads from that consolidate the output of that consolidation exchange uh, uh, as I mean as the input, and then does the sort merge join. So and also I'd like to show you the jobs. Uh, I mean, here since I have enabled adaptive, it is not very clear on how much of shuffle read and shuffle write is there. Mainly from the fact that it has gone into different jobs. Like if adaptive was disabled, you would all see it in one page, wherein you would see that shuffle return is what shuffle is read. I mean, this is just to prove that the consolidation works. I mean, uh, I don't know if we have time, but
Yeah.
otherwise,
We'll give 5 minutes for anyone has any questions to just to go through that. and then we'll move on to the next topic. So, I mean, I'll start from myself, and this is an exciting work that you are doing, definitely. And don't get disappointed if SPIP is not accepted or whatnot. And I would say keep developing and make it pluggable. And if that plugin is working, it depends upon the use case, and mostly. And Caliban might meet most of the scenarios where the shuffle is in terabytes and even petabytes. I know the folks are using it, but this kind of solution can help in most of the use cases. I would really like to see some sort of multi-node executions to see how the shuffle working with, say, S3 or other object storage. And the performance of it. And if mostly think of like the two use cases where spot termination will only give you a couple of minutes before the node goes away. But during that time, this consolidation and the streaming of writing the data to S3, will that be enough for you to write all of the data? That is where I was talking about chunking and how do you handle those kind of situation, specific to interruption of the nodes. But there will be a cases, very rare cases, where the node gets killed for some case, and not during the spot, or could be some hardware failures. I know that is difficult to handle, but keeping those edge cases and mentioning that in your talk to how we handle those kind of edge cases um, would, I think, really help. But yeah, overall, this is great. Thank you so much.
Uh, I just want to add that I think you covered multiple cases around spot and abrupt termination. I think another common thing is executors going out of memory and not being able to serve the
Boom
shuffle. I
kills.
think that's
Mm,
that's also a pretty common cases. Yeah.
yeah, so that's true. It this kind of scenario. Did you think about, is this for use case where you're using PVPVC, or the shuffle is stored in individual nodes in block storage or SSDs? Have you thought about those things?
Yeah, this was not the PVC thing. It was not taken into account, but it was mainly on the SSDs and local storage. Yeah.
Local storage. Okay. Yeah, sounds good.
Yeah, I also said, what Farah just said. I really like this idea. Even if that, it's rejected for some reason upstream, I would love to see this being pluggable. That way, anyone can use it by just, dropping a Java file or anything like that, right? Yeah, because I love the idea. I think there's like a lot of potential here.
Anyone has any questions? Go on. Just okay.
I have a question, and please ignore this if it's a dumb question. I have recently started exploring Spark, so the question might not be relevant at all. But I have been reading one of the AWS document, and where it says to optimize the Spark performance, use NVMe disk for the shuffling scratch space kind of scratch space. So we are recommending to use NVMe disk so that we can get high IO for the read and write for the scratch space. Now, if we are recommending the same, if we are suggesting to move the same shuffling data to remote storage like S3 or else some other Azure blob, wouldn't it reduce the performance?
I can take that question. I think it all comes about it's all about trade-off, right? I think whether you want reliability or performance, raw performance, or it's about reliability or raw performance. Like, for example, if your query is going to run for a day or two, you would want reliability over performance because losing shuffle can make a query that ran for one day to extend it for couple of more hours, which is not what you would like, right? Like, I mean, I understand where like the performance aspects of it, like a query that runs like for 5 minutes. Do you want to use this to make it run for 6 minutes or something? That you would not want. So I mean, it's about trade-offs.
Yeah, exactly. That's a good point. It's all about fault tolerance. Chitragan. So if there are use cases where your EC2 instance with NVMe SSD can go down because there is a spot termination, then you will lose all the data and it has to recompute it. And the job supposed to run for 1 hour can run for another 2 to 3 hours. And if you can't lose and there's a business critical report that you need to generate, then you have to rely on fault tolerance, such as this use case. It's
Got
you don't by default apply to every single thing. This one, you have to identify use cases where you want to use remote shuffle service.
got it. And this is not
And I would like to add to that, just to add to Vara's point, is typically if you can tolerate higher cost of D-type machines which are backed by SSDs, and if you run on demand, then that's the perfect setup where you have on-demand machines backed by NVMe disk, and then your scratchpad and your shuffle blocks get written to the local disk. But in the other world, if you are relying on a lot of spot machines, right? So first the spot market itself is different in different AZ, and D type machines itself are not a lot available in the spot market, right? And the price of the D type machines when it comes to spot is also a lot higher. So as everyone has said that depending on what you're trying to optimize for, if you're optimizing for price, and if you're going in for a lot of spot machines, and still if you need D type machines, you will see a lot of interruptions, and that is where the trade-off of optimizing for NVMe versus something a disaggregated like Calebon or the Shuffle World might be more counterintuitive.
Yeah, 100%. Yeah, thanks, Ed.
Got it. And to keep it simple, then this might not be suitable for a Spark streaming jobs kind of thing at all, right?
That's a good question, actually. If like I think that also comes down to like if your micro batch is like very small micro batches, I would go for this approach. Like this is for a mostly large analytical workload.
Batch.
What I would qualify this for, because having to the probability of a fetch failure for such a small query, a small micro batch, will be very less. And even in case of streaming queries, the shuffle data is not going to explode as compared to the
Batch.
input data. So I would rather not use it in such use cases.
Got it.
But it would I would not say it will not work, but it will still work, but it is going to affect your performance. Like Sid mentioned, it also depends on your the tolerance and factors like that.
Got
Yeah.
it. Okay.
I think that sounds good. We are up to the time, 15 minutes more, and I want to give that time back to Manabu to talk about the next topic, which is Apache Data Fusion Comet benchmark results, and maybe we'll leave the Caliban to the next week. Manabu, don't worry, just only focus on
that's
this.
fine. Yeah.
So before you get started, Manabu, just a statement, right? So we are also evaluating at Comet. Karu himself is doing some benchmarks for our workloads. So yeah, quite excited about this topic, and we would like to share our learnings as well as learn from you.
Oh yeah, that actually be great. Yeah, if you can like share your learnings and then compare notes, that'd be amazing.
Yep.
All right. Yeah, so I've been running a lot of benchmarks with using Data Fusion Comet. For those of you who may not know what Data Fusion Comet is, it is a essentially like a replacement or the I guess a replacement for the Spark's default execution engine. So by default, Spark runs the execution engine within JVM, but JVM can be slow, especially with the GC and all that happening. The performance may not be the best you can get out of it. So the idea is to replace that outside of the JVM so that you can leverage the more efficient performance of other languages like Rust or C++ or whatever have you. So, for this benchmark, I have run the TPCDS benchmark using 1 terabyte of data size. And, really the TLDR is it really didn't perform as much as, I was expecting it to. Especially compared to the gluten and Velox benchmarks we run recently, it definitely didn't, reach the performance I was expecting out of that. So overall, it is about 18% slower when it comes down to the, the absolute numbers. But the again, TPCS benchmark is more about the individual queries. So I looked at the performance distribution for the TPCDS benchmarks. And you see that, 25% of them saw about 20% improvements. And then, 15 of them was about between 10, 20% improvements. And then, 38, like a large portion of this was plus or minus 10%, which I consider to be, it's an okay, performance impacts. And then, 4 of them saw like 10 to 20% degradation. And then 22 of them saw more than 20% degradation. And what is really concerning to me was the degree at which this degradation happened. So I can show you the best performance and worst performance. We'll just go through the worst performance first. So the worst performance actually, performed 1,000% slower or more. There are like a couple of these that are it's just way worse compared to the default one. And we can see that there are others that are performed similarly, like 130% slower. And, I really was surprised by the results. And I had to run it multiple times just to, cover my bases. But this is what I found. And let's see. The improvements wise, I did see quite nice performance results. Seeing like 54%, 30%, all that. And these are somewhat comparable to what we see with the gluten and Velox benchmarks. So there are definitely a lot of promise here, but there are definitely these ones that just did not perform well. And I will also say that Data Fusion or Comet is still going through a lot of changes, and it's definitely still early in the process, but it is one of these technologies that promise to give you better performance. All right, and digging this further, so we found that dynamic partition pruning is not fully supported within Comet. So dynamic partition pruning allows you to essentially not get things that you don't need, like certain partitions that may not be needed for a certain query, and then just don't get that partition and to begin with, right? So if you look at the worst performance one, so query 25, this performed like 1,000% slower. It actually scanned all 2,000 per K files. When you really don't need that many. So for example, if you look at the native Spark one, it only scanned like 30 files. And it's probably what you need to perform this type of query. But Comet essentially scanned 2,000 packet files, and that spent a lot of time. And most of the degradation, this 1,000% plus, came from that, just scanning. And then as for the improvements, they all essentially came to where the CPU intensive workloads are. So like sort merge join, it performed much better in Comet. And this is what I'd expect to be able to get from the Rust-based frameworks here. And then I've also looked at the resource usages as well. expected, the Comet was able to take advantage of more CPU resources here. As you can see here, native Spark, picked around 6 cores per executors, but the Comet was able to use 5 to 9 cores per executors. And that's a good sign because you are using more resources, especially CPUs, because you can burst depending on how much CPU time is available. And it's good to be able to use whatever is available out there. And this is where a lot of concern comes from my side. The memory consumption is significantly higher in the Comet, especially requirement for the off-heap memory. To run the TPC DS benchmark, I had to allocate 32 gigabytes of off-heap memory. Otherwise, the executor just kept going and I just could not get it to complete. This is a very stark contrast compared to the gluten benchmark results. The gluten benchmark that required about 2 gigabytes of off-heap memory, but this one requires 32 gigabytes, and that's just not really comparable in my opinion. So, and then that's obviously comes with the cost implications, right? Now you have to allocate more memory. That means you have to, spend more money on that allocated memory. For example, the default one, I can put all this in this particular instance I was using. I can put 3 executors in that particular node. But with Comet, I can only put 1 in there, and that's just not really efficient. And then I was looking at network bandwidth as well. There's really not that many, differences here. And then storage I/O, again, there's not that much difference here. So, and overall, it's I would say it's a mixed bag. And if you are scanning a lot of Parquet files, it's something you probably don't want to use just yet. I know in the next release, they are planning to add support for the DPP. So that's should give you a lot of performance improvements as far as the benchmarking is concerned. But there are definitely a promise there as well, right? We saw that 50% improvements in compute intensive queries out there, and that's a very, very good sign. And also the main selling point I can see of this particular technology is that it's very easy to get started. All you have to do is just drop a jar file, configure it. That's it, right? That's all you have to do. Now, there are some issues that I ran into. So I was running this benchmark on EKS with the S3 as the storage for the Parquet files. It had a very hard time getting the AWS regions automatically for some reason. As far as I could tell in code, it was making head requests to AWS or the S3 endpoints to get the packet region for some reason. So, you really have to set this region or this configuration that telling you exactly where the region, endpoint region is. Otherwise, it's going to fail with this, exception here. It's just these things that's just took me a while to figure out why this was happening, and just not really good experience. And then I've also seen a very, very excessive DNS query when you are using Comet. When you're using just native Spark, you see about 5 to 10 DNS queries per second. But with Comet, I saw about 5,000 per second, and this hits the Route 53 DNS query limit. There is a limit of about 124 or 1024 packet per second per ENI when you're using the VPC. And when you exceed this number, you're going to get the unknown host exception, and this really can mess up your jobs. So you want to make sure that this doesn't happen. And with DNS queries, with Comet, I was constantly hitting this limit. So to mitigate this, you really need the node local DNS cache. This is let's see here. So this is the solution provided by the Kubernetes. So this essentially allows you to cache the DNS results on node instead of just going into your DNS servers like core DNS. Let's see here. Oh yeah, and then finally I just covered the memory requirements earlier, but yeah, it's definitely a concern here. Uses a lot of memory, and it's something that you have to think about. But yeah, that's the results I've experienced. So I would love to see others run the same benchmarks or something similar, so that we can compare notes and just make sure I'm not doing something wrong and all that. As for like next steps, I will be running the same benchmark in the next release of Comet, because that seems to be the most promising one as far as the performance impact is considered. So yeah, that's what I'm going to be doing.
Yeah.
If you have any questions, I'll be happy to answer.
Thanks, Manav. We got 4 minutes, and if anyone has any questions, let's talk about it. Maybe Sid, the work that you guys have done, maybe we can present that next week and go deeper into this topic.
Yeah, absolutely, Vara. So first of all,
Yeah.
thank you, Manabu, for sharing this. Right, great insights. We are still very early in our journey. Right, we have reached a stage where we will soon be able to run Comet against our benchmarks, and then Karu will be able to, maybe in our next call we can have some more details based on our benchmarks, because our workloads will also be using the iceberg layer. So we will see how it behaves with iceberg, because when we tried Gluton Velox, even though it showed a promising native acceleration, but since we own our own custom iceberg layer, so we were not seeing a lot of operators falling back to Velox over there. Most likely we will see the same symptoms in Comet as well, but that is still TBD. Yeah, that is all from our end. Kuru, do you like to, do you want to share any initial experience of using Comet?
No, actually, like you mentioned, we are still in the early stages. Like, I mean, I hit some issues related to how I have to build from source for various environments, but I mean that is I mean that is not a real issue. But one thing I wanted to ask Manabu is like, I think when someone comes for, I mean when someone wants to use a query accelerator, it's generally an evaluation between Comet and Velox, right? I think if you are able to add another column to your to these benchmarks which compares native Spark, Comet and Velox, or just Comet and Velox also, would be very useful, is what I think. So that is one feedback. But on the other side, the experiments that I'm doing, I will keep you all posted. Probably if I have some updates next week, I would love to share that.
Yeah, that's correct.
Yeah, Manabu, just one, maybe question or a suggestion, right? So when you said that the overall performance of a few queries was not optimal, if you get a chance, can you also share, since dynamic partition tuning was not enabled, is not working, and it is pulling in a lot of Parquet files in memory. So is it because of the source reader which is queuing things, or if you just compare these stages where the shuffle happens, and if you just compare the difference of native Spark shuffle versus a Comet shuffling. So do you see that, yes, a shuffle might be outperforming, but because of the input source reader discrepancy, it is queuing the entire result?
Yeah, that's a good question. Yeah. I was gonna show you all the events better, but maybe I can do it next time. But yes,
Okay.
I actually saw improvements in the Comet scan parquet compared to the native parquet. So there's definitely promising things in there, right?
Yeah.
But it's just that right now, it's just the performance impact is dominated by the
Yeah.
fact that it doesn't support TPP.
Cool.
Yeah.
Maybe probably we just wait for dot 14 and see what the findings are.
Yeah.
Yeah. Yeah.
Yeah.
I think the Comet is mainly designed to scan those Parquet files for sure compared to, but in Velox case, and I think it relies more on Spark Native. But we can show the comparison, like you said. I think we do have comparison showing the native, Vlogs, and Rapids. We just need to add the Comet results to that. I think that table has all three of them below. Yeah, there you go. There's a table with the results, and if you scroll down, here. Yes, one. That's a native gluten rapids, and maybe we can add Comet as well, so that we can look at the individual queries and where it is performing, which one is poor, and then we can go back to that query, what query is doing. But I think in summary, anything which is related to heavy joins and aggregations and data fusion suffers with the large shuffle data. But the gluten works on that case. But there are so many things like Python UDFs are not supported in both Java UDFs, and Python UDFs not supported in both data fusion as well as Vlogs as well. Some window operators, they're still both the tools needs to add support that is meets to native Spark, and data fusion falls back most of the time to native Spark.
Yeah.
I think we are 2 minutes over. Sorry, Andre, I know you raised your hand.
Yeah, it's fine. We can talk about it next time. I just
Yeah.
wondering because I noticed that it looks like the diffusion consumes a bunch of memory, right? Compared to Velox and others. Did you try to connect with Andy and other folks in the diffusion to ask why it's happening?
Yeah.
I think the only thing I can think of, like, the Velux is a C++ engine and Data Fusion is a Rust engine. I don't know between these two engines which one is more memory hungry.
Okay.
So what I know, so just to Andres' point, right? We are looking at all these benchmarks, point in time, right? But then, it will be also nice to understand from a future-proofing point of view, which project has got, better community support, adoption, right? Because if let's say that the comment community in Apple, right, and Andy, Parth, and Matt, if we have a lot of contributions, and if they are looking into financing, and if they have a better future roadmap versus what is been happening in Common Gluten, it will be just good to know, right? From a future proofing point of view, what should we bet on?
Yeah, I think it's definitely a good idea. Maybe I should reach out internally to Andy and other folks to see if they have, a plan, because I know there are a lot of interest in data fusion, and I know it's actively being developed. I don't have visibility on the roadmap, but maybe it's something I can follow up for. Yeah, but
I'm not part of the data fusion community, but do you have any other vendors other than Apple contributing to it today? Like maintainers or contributors heavily outside Apple?
I saw a lot of engagement, outside of Apple on data fusion. I'm not sure about contributions, but I can definitely double check on this. But I
think
think the community is growing here.
Yeah, certainly. So going back to the set point is the open source solutions with Gluten or data fusion, it should never rely on a single organization to maintain it for a longer run, because organization can have lots of changes over a period of time. It can be AWS or it can be any company. That's where we need to get to.
Yep, absolutely.
Okay, cool. Thank you so much. And I think we have 4 minutes over. This is really good. And the way these conversations are going, I really like we didn't talk about Spark Operator much, but we are talking about a lot of Spark optimizations, and I love it. And I hope people will love it as well. And maybe in the next week, we will continue this conversation and talk about Apache Killibon best practice and compare with what Salesforce presented today. And I also would love to talk about the new feature that Spark added, which is is it data pipelines or something like that in 4.2.4.1.1, the latest
It
version?
is declarative.
Declarative pipelines, yeah. So that would be interesting to talk about, and hopefully see if you have a time we can demo that.
Thank you so
All right.
much, Michael.
Thank you all.
See you
Cool,
soon.
guys. Thank you all.
Thank you all.
Thank you so much. See you soon.